Well, very much. So good to see you all here virtually. Uh, although I'm now an emeritus professor from the University of California, Santa Barbara, uh, my wife and I actually are in our home in southern France. So this is a good time of the day. It's about 1 o'clock and lunchtime, and we're ready to have just maybe a very short little conversation or description of a bit of an adventure, a bit of an exploration that I've undertaken recently in collaboration with Elena Panagiotou, who is a professor at the University of Tennessee in Chattanooga, where it's, of course, not a convenient time for her, I think, at this point. But what I'll describe was stimulated by work that she talked about earlier on in this session with Lou Kaufman, stimulated by work with Lou Kaufman, and an idea and a strategy that goes back to 2005, designed to help us understand the knotted structure of proteins, which was joint work with Akash Dubey, a postdoc of Andrzej Stasiak, who has now also just retired in Lausanne in Switzerland. So there's a long shaggy dog story here, as I'm notorious for telling. Of course, the Conway and Kinoshita-Terasaka knots were of current interest just because of the new results in the last couple of years that provoked at least my attention and the attention and appreciation of most all of us in knot theory, resolving an old question as to whether or not the Conway knot was a slice knot or not. So anyway, let me, for those who may not be nearly so much amateurs of the Conway and Kinoshita-Terasaka knots, start with a little historic description and then spend a few minutes talking about the sort of the ideas that we've been exploring recently. Now, I need to somehow figure out how to change my screen. There we go. So the Conway knot and the Kinoshita-Terasaka knots are 11 crossing non-alternating knots. And all of their sort of classical, now I say classical in terms of Alexander, Jones, Humphrey, Kaufman, all of our knots invariants from polynomial invariants are unable to distinguish them. So they have Alexander polynomial 1, and they are the smallest such knots with Alexander polynomial 1 in the sort of currently popular useful Thistlethwaite-Dowker, Thistlethwaite notation or tabulation. They are 11N34 and 11N42 respectively. They are, hopefully if I remember so these are the pictures you see in the knot atlas and maybe in the sort of online knot tables using the Thistlethwaite minimal representation. But for those of us of a certain age, let me say, the more familiar representations or presentations are the ones that are shown here on the gate of the Newton Institute of Mathematical Sciences in Cambridge, England. These are, and I'll have another picture of these are 11 crossing presentations as well. And my colleague, collaborator, Raymond Licorice, was in a high-level administrative position in England when the design of the Newton Institute and Math Sciences Institute and Gates and so on were under consideration. And he proposed that these two presentations in honor of John Conway, who was there for many years, be part of this gate. And they are there today. And The next picture will show them as they are represented here, I believe. Right. So these are the two presentations that were constructed in the medallions on those gates. And the two knots are related by an operation called mutation, related to sort of tangle theory and skein theory, which I really learned from the work of John Conway way back when. And in the circles at the bottom, you see two-string tangles. And the outside of these tangles, the exterior are precisely the same, isomorphic, and the tangles are related by a sort of 180-degree rotation, or if you wish, just flipping your hand over like this. So this is an operation called mutation. And so one of the things that Ray Licorice and I proved in our paper about these Humphrey polynomials is that mutations doesn't change the polynomials. The Jones polynomial, our polynomial, Kaufman, because we're able to do a sort of multilinear algebra argument involving bases for the skeins of the two-strand tangles. This works really well for two-strand tangles because they're so simple. Analogous things for more complex tangles, unfortunately, are more complex and less effective in proving simple results such as this. So how do we know that these knots were different? Well, let me see here. With any luck, that'll be the next thing. Oh, well, this is just another picture of mutation coming from Wolfram. So mutations aren't kind of like unique. There isn't a sort of simple, unique way of doing a mutation to relate these knots. There could be many mutations. And in fact, I don't even know how many maybe really distinct kinds of mutations exist between these two knots, the Conway knot and the Kinoshita-Terasaka knot. The Kinoshita-Terasaka knot, it goes back quite a ways actually, and the Conway knot similarly. So these are really been part of knot theory for many, many years. And so here's just another one I found looking on the internet and looking for representations of these knots, and this is due to Weisstein in sort of in the math world or mathematical world, something of that character. And anyway, mutations have lots of, are likely to have different ways of manifesting themselves even between the same two knots. In 1971, so this is like just after I got my PhD, Bob Riley was studying the knot group, the fundamental group of the complements of these knots. And he was able to, he was really a pioneer in this actually, was able to show that the complements had to be different because they had different representations, different finite representations of the fundamental groups of their complements. And so this was a real, turns into, or has been developed into really a powerful tool for studying knots and their, by virtue of studying their complements. Somewhat later, in 1986, David Gabai proved a theorem that showed that they had different genera. The genus of the Conway knot is 3, and there is a picture of a genus 3 surface from one of Gabai's papers, actually, and a picture of a genus 2 surface. You can, it's, how to say it, it takes a little bit of a work to go from a presentation of the knot to pictures which give these surfaces. What makes these surfaces, how to say it, how does one know that these surfaces are of minimal genus? this is really the powerful work of David Gabai in his thesis under the direction of Bill Thurston. He was able to prove that there existed foliations of the complements of the knots, in which this was the single compact surface. There were no RAID components, so there's no tori involved in this, so you have to eliminate those. And Thurston's had proved the theorem many years before that showed that under such circumstances, the surfaces had to have minimal genus. So this was like the first really sort of geometric way of successfully getting the genus of many, many knots, and was able to sort of distinguish these two knots. Okay, so that's a bit of the history. I believe, I'm not wondering if I had anything more to say about this history. I wanted to show you these surfaces because you have to know where to look. They're not easy to find, at least in my, and here I am in southern France and all my books are in Santa Barbara, so I couldn't even look in the classical knot books. But if you're looking for this, here they are. And I can, how to say it, recommend them to you. And I've been having a lot of fun just exploring their consequences and what one might make of them. Oh, all right. In doing so, let me just call your attention to an absolutely wonderful lecture by, I think it's Jennifer Hom, who gave a lecture about Lisa Piccirillo's new theorem showing that the Conway knot wasn't a smoothly sliced. This is, I think, a publication now with the AMS, maybe in one of their notices or something of this sort. But anyway, this is a wonderful lecture that you can find that she gave, in which you find the picture that I'm showing you here, which is a slightly reorganized picture, classical picture of the Kinoshita-Terasaka knot, showing that it's a ribbon knot. So we didn't know whether or not the Conway knot was a ribbon knot or a slice knot, but if you know that a knot is a ribbon knot, that is, it bounds an immersed disk where the intersections are of the sort shown in this picture. They're sort of like bands where the whole disk pierces itself in different ways. And so if you have this situation in the three sphere, you can just push off a little bit here into the four ball and remove those singularities and show that you have a smoothly sliced knot. So this is a really quite charming picture here for the Kinoshita-Terasaka knot. And in fact, then Lisa showed in a very powerful argument that just appeared maybe a year ago or so, maybe last year, maybe the year before, in the Annals of Mathematics, showing that that one could not get such a structure or even anything more complex for the Conway knot. So, so those of us who've known these knots for a long time, like myself, sort of think, why is it that the Conway knot is so much different than the Kinoshita-Terasaka knot? What is it about this structure? Is there something about this structure that we can observe that would explain to us why there's such a difference? So that's what got me thinking, and using some ideas, as I say, that go back to 2005, and a recent a model from Clay Schonkweiler and his student that they published just a couple of years ago, in which they tried to find minimal equilateral polygonal models for various knots. So this is like a computer search using various strategies, models that Schonkweiler and Jason Cantarella developed using symplectic topology and representation spaces and so on. So they produced these 11 edge equilateral models, which they kindly gave me the coordinates for. And then I could sort of fatten them up, make them as thick as possible, sort of move them apart so there is sort of as in the nicest possible position. And the pictures I show you here are just what I got on my computer, wiggling it around. And this is not any, these are not optimal configurations, but we have data here, configurations in 3 space. That's what makes this sort of useful for me in the following way. Let me see if I have the next slide right. Yes. So going back to 2005, what we developed to study proteins. Proteins are macromolecules who are represented by geometrically their structure by sort of open arcs in 3 space. And we wanted to capture the knotting of those. And the strategy was to take this kind of chain here that I've described with two endpoints. And then from those endpoints, take rays going off to infinity, as we said, well, in fact, off to the boundary of a sphere of some gigantic radius, and close them up. So if you close these things up, of course, you have a closed curve and you can calculate your favorite knot polynomial or knot invariance. And so that's what we proposed. That's what we proposed to do by doing this over all possible directions. So there's no bias. It's sort of like a Keplerian approach to this. So that gives you a 2-sphere. You can imagine a huge 2-sphere in space. For each point, you have, it represents a closure of this arc in a sort of a small toward the center. And you can assign to that point the knot type of the closed curve that is resulted. Well, what we do then is do this all around the 2-sphere. This turns out to be a very nice operation, which is well defined except for a set of measure 0. And so it gives you a basically locally constant designation of a knot type across the 2-sphere. Well, that gives you a probability distribution, and you can look at the probability distribution and to get all sorts of information as to whether there's a dominant knot type, which you might assign to your protein structure, what is the spectrum of knot types, if you wish. So on the right here, I've shown for this sort of simple polygon, a histogram of the spectrum of knot types, where you see that the dominant knot type is really the unknot, and there are a few trefoils in there. Typically, for proteins and for, in our case, that I'll talk about, the structures are more complex. This method, how to say this? This method picks up how things interact with each other, because here in this picture, you see the rays going off to infinity, and they don't sort of, the rays don't interfere with, don't have a consequence with the rest of the configuration. But if you bring them forward, you can see they start winding through the configuration and picking up lots of who knows what kinds of structures of knotting, representing how this thing interacts with itself, sort of self-interactions that lead to a variety of knotting. And it's that part, that aspect of it that we want to exploit. So what you can do, and this is what Eleni and Lou provoked me to realize, is that instead of just looking at the statistics, at each point where we have a knot type, we have a polynomial, and one can integrate those polynomials over the entire 2-sphere, this probability distribution in the 2-sphere, and you get an average invariant. In this case, the average Humphrey PT invariant. And so this is what you get for that very simple configuration. And you see the constant term there on the left 0.9981 is really a signal that the dominant structure of this simple configuration is the same as that of the unknot, whose polynomial would be 1. Anyway, one can, and I still do even today when I was outside working in the woods, think about various ways in which this kind of approach is going to be related to the spatial structure of your knot. That's the mystery. That's like the, the whatever dollar question that is. How to extract from this strategy relations about the structural character of your configuration. Okay, so one way is to look at this sort of average Humphrey polynomial. Now here, I've gone further, and I'm probably, I talk forever. So here's the idea. We have these 11 edge eddy Schrank-Weiler configurations. How am I going to get some information out of that? Well, for each of the 11 edges on each of the 2 knots, I remove that edge and I do my 2-sphere configuration over all directions of closures and get a spectrum of knot types for that particular edge complement. Well, then I do that for all 11 edges and I amalgamate all of those. And so that gives me something, a sort of spectrum that's associated to the configuration, not just the complement of a single edge. And I do that for both the Conway and the Kinoshita-Terasaka knots. Okay, so this is like, totally wild and crazy computational effort. I should tell you that I have to remember what study this is. So I typically like to get several thousand closures for each of these. So you get a huge data collection and a huge opportunity to do data analysis like big data. Here are the spectra, though, of those two data sets, one for the Conway in blue and one for the Kinoshita-Terasaka knot in red. And it's sort of like, oh my goodness, now we're looking at, this is like physics, experimental physics. Now we're looking at a signal here, and we can see that these are really quite different. The Conway knot in blue and the Kinoshita-Terasaka knot in red. Okay, how can we capture, question to myself, how can we capture then the fact that these are distinct in a way? Hanging out with biologists a lot tells me that they're not going to like this all that much. They're going to look for something really, like a number or something that's going to help identify what we've got here. So I pushed myself a bit further, thinking about spaces, vector spaces of knot types, things that one can do with that, and here's what we get. Well, first, we get the superposition, if you wish, or the average over all these closures of the Conway knot. And by gosh, that looks like a lot of data that's in there. And we just see, let me see if I can spot it in here. Right. In the second line, you see something without any exponents. So that 2.29. So that would be the place where the unknot would lie. Somewhere buried in this is going to be the Humphrey polynomial of the Conway knot. And exactly how that lies in there is a very interesting challenge to try to tease out of that. But I'm not going to go into that. But it's in there someplace, and it's got to be in. It has to have a signal in there that's relatively substantial, having to do with its spatial properties. Similarly, here we go for the Kinoshita-Terasaka knot, and that same constant term, rather than being as it was, excuse me, while I go back, 2.29 is 1.33. wonder what that's telling me. That's the kind of analysis, kind of the question that this kind of approach leads you to explore. So how to simplify this? I'm hopefully getting close to the end of my, 14 or 15. Okay, so I've got these big polynomials. What is the most, for me, the basic way to distinguish between two variable polynomials? Well, I call it the spread, but here's what you do. A two variable polynomial has, of course, two variables with different exponents. Those different exponents can be used to identify positions in a two-dimensional integral lattice. And at each of those points, you have a coefficient, so you can assign that coefficient as a value to that point and produce for yourself some like a physical cloud with positive and negative values, let's say. So it's like a, how to say it, you're at least I'm interested or led to thinking, okay, well, let's think about the center of mass of that, okay? So maybe I put in the absolute values so that I don't have any negative masses. But anyway, find the center of mass. And then in the sort of mechanics part of the world, then you want to know about the squared radius of gyration, or the radius of gyration of this physical system measures how it's spread out. So if you think of your polynomial as being a cloud in the integer lattice, then how much is that spread out, and what is the character of that cloud? And is it sort of ellipsoidal? Is, there's a geometry. So anyway, you can compute the squared radius of gyration, and so if it's very small, that tells you your polynomial is very compact, okay? And so for that simple chain that was very much like the unknot, the squared radius of gyration is 1.08431 sins of computing. And what happens for here? Well, for the Conway knot, the squared radius of gyration is 119, whereas for the Kinoshita-Terasaka knot, it's like 37. So that's curious. Somehow this polynomial spread is telling me that the Conway knot is really significantly more complex than that of the Kinoshita-Terasaka knot. Well, that sort of, fits with our bias here in terms of how we think of one being more complex than the other. Now, you can, of course, look at the difference between those polynomials and compute the spread of the difference, which is 90. So that's tells you they're really quite different. Okay, wonderful. So they are in fact different, even though the configurations are different, even though the polynomials of the closed configurations are identical. Somehow this has captured some aspect, some feature of the structure of those. Exactly what? Well, like with all these knot invariants, exactly what is being captured is, of course, the big question, and how to exploit that and so on. Anyway, according to my notes, that was where I stopped my sharing, and I'd be happy to hang around and answer questions and speculate about things. This is like, for a retired knot theorist in southern France, this is like infinite amounts of opportunities to speculate, to explore, to guess, to imagine, and what great fun. Anyway, thank you very much for your attention.
Well, I have a question. How do you think that the distributions would change and the spread of the polynomial will change if we consider a different configuration of the knots?
Okay. Well, this is how we do research, Lena and I. I don't know. First, because I need 11 edge, or I need polygonal representations, okay? And so it's very hard to modify those in ways that, I don't know how to modify those in ways that would be interesting to test any conjectures I have, first. Second, as I was mentioning today, I was out working in the woods here, removing oak trees that are shading our olive trees. But in any case, and got to thinking that one of the things that one needs to do here, why not, is think about your configuration. Okay, so it has a convex hull. Let's put it that way. It has a convex hull, and on this convex hull, there are sometimes edges of your configuration, okay? So if you have an edge on the boundary of your convex hull, then there is a plane that cuts off like half of space in which there's no part of your knot. So that cuts off some proportion of your two-sphere of directions, so that any closure using those directions is going to give you the constant polynomial. In this case, it's going to be, let's say, the Humphrey polynomial of the Conway knot, okay? Well, so those places where you have these planes cutting off half of space that's going to have constant knot type, you can generalize that. You're thinking of smooth configurations, and where you have tangent planes to your knot, similarly cutting off half of space. So if you have a little tiny kind of closure, a little gap in there, any closure in those directions is going to give you the same polynomial. So for sure, there's going to be some substantial, let's say, some interesting amount of contribution of the polynomial of the closed configuration that might depend, is likely to depend, and to what extent, that's the question, on the specific configuration, okay? So if you change configurations in this way, you're going to likely change very significantly the average polynomial that you get. Okay, so anyway, so that was my brilliant work out there in the woods when I'm working on cutting up oak trees and so on, thinking, is there some way to quantify this? And is this maybe, the ideas you get working out in the woods aren't always the most brilliant ones. Is this something that people have thought about a long time ago and I just don't remember what it means, what it's called? Because this is like geometry. It could go back to, to the 60s and 70s, where we had lots of theorems about doing integral geometry with knot configurations. So I don't know. And here I am spilling the beans to you folks, not having thought about it even over lunch. But that's the kind of thing I would say to you. We would first want to look for something like that. That's got to be the simplest thing to try to get your hands on, and to try to find useful configurations to test that on. Well, that's a bit of a puzzle, because the ones that Clay and his student provided, of course, are very, very special. Right. So anyway, so it's an interesting question, and I really don't know, but that would be my current best bet about a way to try to get at this, to figure out where to what extent are we going to see the Conway knot polynomial in these two in the average configurations? That might give us, if we can measure that, that might give us a bound on something about its exposure. If you want to follow that. Okay. Anyway, wonderful question, as usual.
Thank you.
Since I was thinking about something like that this morning.
Very interesting.
Initial presentation of Conway Kinoshita knot and Conway knot and Kinoshita-Terasaka knot with a stick presentation of the same length. Is that a coincidence that Conway polynomial and Kinoshita-Terasaka knot has the stick number the same, or it depends on the mutation stuff? I think it's a coincidence.
I suspect you're right, but no one knows. There is no theorem. There is no theorem that says you cannot have a stick number 10 presentation of either of those knots. It's just that with millions and millions of tries, they did not see one. Yeah.
So if we change the presentation and the initial configuration of a fixed knot, then the average polynomial will be quite different when we move the configuration.
I think so, but here is you suggest a good question to me that I don't know what to do, and that is I don't know how to realize a mutation when I have a very simple, minimal kind of stick representation, because there you've lost, so far as I can see, just looking at it from different perspectives, you've lost the opportunity to try to do a mutation of the sort that Conway proposed. Yeah, I don't see how to realize that. You need a kind of way to separate out the two tangles when you have a polygonal presentation of a knot. And at least in these two cases, looking at it, rotating it, I couldn't see any opportunity to do that.
So it's like
Excellent question.
Taking the intersection of the Conway sphere and the knot, and we allow the stick bent at the intersection of the knot and the sphere. And we make the stick presentation inside and outside of the Conway sphere independently. Then we may be able to have the stick presentation of a mutation pair of knots.
Right. That's an interesting way to go at it. Rather than trying to use the presentations of Schonkweiler and Eddy, create new ones which are adapted to allowing for a mutation. Very, very interesting idea. The what is it called? Knot plot sometimes lets you create and maneuver that a little bit better. So that might be a way to get a sort of opportunity to do that. Yeah, excellent idea. Yeah, thank you.
Thank you. And I also thought it might be interesting to fix a knot instead of comparing two knots. Just fix. Instead of comparing two knots, think of one knot and make several configurations of that particular knot and take average polynomials. Then they must be different. And then, for example, when the knot has unknotting number 1, we see the particular crossing to change. If the crossing to change is obvious, then the polynomial may be close to the unknot, because if you remove the arc near the crossing to change, I think the possibility is high to obtain some polynomial like the unknot. So I wonder if you may try to examine a fixed knot instead of comparing two knots. to detect some nice configuration for that knot. In that case, my question is, how long does it take to calculate the average polynomial for fixed configuration? Like 3,000 configuration, how long does it take by computation? I wonder.
Well, so in my case, let me think here. So it's quite fast. So if I took, so it depends on your situation, but I like to take somewhere in the order. So how do we do the closures on the two-sphere, right? Initially, I thought one should do them randomly, but I've now learned better. You want to do them with respect to some uniform distribution of points. This is a question of like numerical analysis. How do you do numerical integration most precisely and most rapidly? Well, in this setting, you find a uniform distribution of points on the two-sphere. And so that's a sort of challenging problem of numerical analysis, and you can find examples where people have actually pre-computed those. I'm trying, the numbers I used some years ago were always squares. So there may be, 4,000 points or something like that, or 16,000 points. So you can do that with that set of points very rapidly. But you don't want to, of course, always do it with exactly the same points. So what I would do is do a random rotation of that collection of points on the sphere. And so that actually goes relatively rapidly because I've got this old Fortran program from the 1980s that calculates the Humphrey polynomial very quickly. And so long as your configuration has fewer than 250 crossings, it's fast. On average, it's fast. And so, okay, that works out very well. And Morwen Thistlethwaite wrote me a little program letting me simplify knot presentations, which usually gets them down to fewer than 200 crossings or even smaller. Sort of using Reidemeister moves in cunning ways. So that goes very quickly. Where it takes time is when I've extended this to the case of links, and there then everything squares and the time squares, and that can take days. But for knots and only a couple thousand closure points, it's like very quick. So yeah.
So
But
do you apply parallel computations? Do you apply parallel computations? So each time.
No, I don't. I just use my little MacBook Pro here. Bruce Ewing, this fellow who was a student working with me back in the 1980s, and I wrote a version of this that did parallel computation. And because we didn't know what we were going to do, and we had parallel computers were newly available at UC Santa Barbara. So we had one with like 128 processors that we tried on, and it was like shockingly efficient. The parallel implementation of this is like shockingly efficient because it sort of uses all the 128 CPUs as soon as you start changing crossings and spawning off subsidiary calculations. We created a method called a load balance calculation, namely for the Humphrey polynomial, you have to change crossings to simplify the knot. And so the choice of which crossings is really, really important. And we chose to do that in such a way that, for example, if we had an unknotting number 1 knot, we probably wouldn't change that crossing that we could unknot it with. We'd change a different one because on average, it would have the biggest impact on the simplification of the calculation. So there's a whole computational science kind of side to this thing that works out really well when you do a parallel implementation. But I'm like 50 years away from that or 40 years away from that. I haven't thought about that in a long time. But that was what our observation was, that if for some reason you wanted to go and get serious about these things, of course, what I can't say is this is any better than doing any of the more contemporary ways of the work of the sort of new invariants of knots and so on, using spectra and spectral theory and so on. This is just really classical. So it works really well for this. And here, I would be tempted to actually, rather than use my old programs, go and rewrite something that might use a Alexander polynomial, because that might speed up some things a little bit. But what's missing here is the relationship between this kind of analysis and the spatial properties of the configurations you're studying. I think that's the part where my interest lies. And so as we're talking with Elena here, how to interpret, how to extract information and exploit it. That would be the idea. Whoops.